Right. In this video, I'm going to be working some absolute extrema examples, and this is going to be solutions to CalBC Homework 3.3. So, the first one is just going to be, okay, where is the absolute maximum going to occur on the closed interval 0 or -2 to 4? Zoom in a little bit. It's right there. All right. So, I'm going to run the closed interval test, the candidates test. Okay, so the first step is to identify the critical point, so I'm going to take the derivative. Okay, that's f prime. We need to know where the derivative is 0 or undefined. This is never going to be undefined, so I'm interested in where it's 0, and I'm going to factor out a 3x. I'll be left with an x minus 2. Okay, so my critical points are x equals 0 and x equals 2. Right, and then so I'm going to make my little table. I'll have x, and I'll have f. Okay, the x values that I'm interested in are 0, 2, -2, and 4. All right, and so I'm going to plug into f in each of these x values. So f is -2 to the third is -8. Minus 3 times x squared is minus 3 times 4, so minus 12 plus 12. And we want the absolute maximum. This is a negative number. I somehow think that's not going to happen, right? Okay, at 4, I'll have 4 to the third. Yeah, that's 64. Minus 3, okay, hold on. 64 minus 3 times 16 plus 12. Okay. Maybe. When x is 0, f is going to be 12. That one's easy. And then when x is 2, I'm going to have 8 minus 12 plus 12. Okay. Now, which of these is the largest value I see? I think the 64 plus 12 minus 48 is definitely bigger than 12 and bigger than 8. So it's going to, this is the maximum value. But they were asking what was the x value where that happened, and that was at 4. Okay, so I would say on the interval -2, 4, f takes its maximum value at x equals 4. So that was an endpoint maximum. But I'm sure there's enough examples on this set that you're going to see some interior critical point maximums as well. All right, number 2. Let f be the function given by another third degree polynomial. What's the maximum value of f on the interval 0 to 6? Okay, we'll do that. Let's skip that a little bit. And okay, so f prime is 3x squared minus 12x minus 15. I can factor 3 out of all 3 terms. Times x squared minus 4x minus 5. This is again something I can factor. All right, so I'll say f prime equals 0. That's x equals 5 and x equals -1. Okay. The closed interval that I'm interested in is 0 to 6. So that's going to be outside of my interval. I'm not interested in that. So what I'm going to do is I'm going to consider x and f of x. Okay, the endpoints are 0 to 6. And then the critical point that I'm interested in is x equals 5. And we're going to run this through, except, oof, man, I think 6 to the third is 216. Well, 30 times 6 is 180, and then 6 more times 6 would be that 36, so you got 216. F 0, 0, f of 6 is going to be 216 minus 6x squared. Well, that's x to the third. Or that's 6 to the third, right? 6 to the third, 6 times 6 squared. And minus 15x, so minus 15 times 6. Hold on. All right, and then at x equals 5, I'm going to have 5 to the third is 125 minus 6 times 5 squared. Wait, that's going to be 6 25s. 6 quarters is $1.50. And minus 15 times 5 is 15, 30, 45, 60, 75. Okay. Well, that's negative. That's definitely negative. So I think the maximum value of f on the interval 0 to 6 is at x equals 0. But they didn't ask about where the maximum value occurred. They asked what the maximum value was. Now this, coincidentally, the maximum value was the same as the x value of the location. What's that? I mean, that's just a coincidence, right? And probably I wouldn't ask that on the free response because I don't want you to be right for the wrong reason. So what I would say is the maximum value of f on the closed interval 0 to 6 is f of 0 equals 0. Now, this is maybe one that if you had looked at it, okay, let's think about f prime right here. You know, I'm going to sketch the graph of f prime. It's equal to 0 at -1 and 5. And it's a second degree polynomial with positive leading coefficients, so it's going to make a parabola. And like here's 0 to 6. Okay, you can see it's doing a lot of decreasing between 0 and 5. And then it only has between 5 and 6 to increase. Now, we don't have the tools to know exactly how much it increased by. Okay, but it does seem reasonable that the absolute maximum would happen at 0 because I just did a bunch of decreasing and then I did a little bit of increasing after. Okay, so it seems reasonable. Okay. Number 3, an object is traveling with velocity given by v of t, which is a third degree polynomial in t. What is the maximum acceleration of the object on the time interval 0 to 3? Okay, well, I'm going to need to find the acceleration. Acceleration with respect to time is the derivative of velocity with respect to time. So dv dt, and that's 3t squared minus 6t plus 12. Okay, that's the acceleration. If we want to maximize the acceleration, we need to start with the critical points of acceleration, and then we will, and to do that, we're going to need to take the derivative of acceleration, right? This is the situation where you would take the derivative of acceleration is to find a maximum or a minimum acceleration, which actually could be a thing that somebody would be interested in because we know that acceleration is proportional to force. There's only so much force that, living things can take. And so, when engineering like flight, space travel, things like that, you need to be aware of the maximum acceleration a person can handle or the maximum acceleration of a given path. So, because it's proportional to the amount of force, to the maximum amount of force. So, okay, anyway, acceleration prime is going to be 6t minus 6. I like that, because a prime equals 0 at t equals 1. We're interested in the closed interval 0 to 3, so t and a of t. My candidates are 0 and 3, the endpoints, and the critical point that I've found is 1. All right, and then the acceleration is is 3t squared minus 6t plus 12. So that's going to be 12, 3, it's going to be 27 minus 18 plus 12. And that's going to be bigger than 12 because 27 minus 18 is bigger than 0. And then at t equals 1, I've got 3 minus 6 plus 12. Okay. Both of these have the plus 12. This is a negative 3, and this is a positive number, so I'm going to conclude that that's the maximum acceleration. Uh, 0 to 3. And we can do the arithmetic, or we could just not. So I'm going to say 27 minus 18 plus 12. 21, maybe? Not worth it. Okay. Oh, number 4. Function g is given by another third-degree polynomial. Oh, man. It must be a pattern. It must be like a reason I put all those third-degree polynomials on this homework. Okay. What's the absolute minimum value of g on negative 2 to 1? All right, well, g prime of x is equal to 12x to the 2 plus 6x minus 6. What? Why would I do this? Why would I do this to myself? It's okay. I'm going to factor out a 6. 2x squared plus x minus 1. I don't think this should be that hard to factor. Okay, I'm going to need the plus 1 to be over here to go with the 2x, so I can end up positive, and then that'll be minus. Okay, there are other ways to factor this, but what I'll tell you is the ones that you would have to factor on, say, a quiz or a test or on AP exam, vast majority of them are just going to be the easy factoring, like everything we've seen so far. All right, and all right, what am I doing here? Oh yeah, I'm going to say g prime equals 0 at x equals a half and x equals negative 1. And of course, both of these happen to fit in my interval. I was hoping maybe we could exclude one of them again. I like that. All right. So my endpoints are negative 2 to 1, and my critical points are a half and negative 1. I'm just going to run through. Oh, whoops, not f. G. All right. 4x to the third. X to the third is negative 8, so negative 32. Plus 3 times x squared is 3 times 4 is plus 12. Minus 6x is plus another 12 plus 1. Okay, when x is 1, I've got 4 and 3 is 7, and 1 is 8, minus 6 is 2. Okay, that's some arithmetic I can do. X equals a half, that's 4/8, plus 3/4, minus 6 halves, plus 1. And I'm still feeling like this is the most negative number I'm seeing so far, but you know, we'll just make sure. And at negative 1, I've got, nope, 4, so negative 4. 3x squared, so it's plus 3, plus 6, and plus 1.
How are you?
Okay, I had to go to a meeting. I lost my place. I can see that I'm taking the absolute minimum value of g on the closed interval negative 2 to 1. I've filled out my candidates chart. And let's see, what is the minimum value of g? All right, let's see. Any of them negative? This one feels like it might be negative. 24 and 1 is 25 minus 32 is negative 7. Okay. And let's see. Now this one couldn't be negative 7 because the most negative I've got is negative 3. Same over here. Okay, so this is the minimum value. On the closed interval, what was it? Negative 2 to 1 is g of negative 2 equals negative 32 plus 25. And that'll be all. Number 5. The derivative of function f is given by f prime equals e to the negative x cosine of x squared. I'm going to need to get a calculator out for this one. I probably should have mentioned that. Well, I suppose that you could know that cosine is strictly positive on the interval negative 1 to 1. 1 radian is 1 radian is less than pi over 2 because pi over 2 is bigger than 1, pi being bigger than 2. So you could do it without a calculator, but what I'm going to do is I'm going to pause for a second and grab my calculator. And so what I'm going to do is I'm going to graph e to the negative x cosine x squared. Okay, I'm going to make sure I'm in radian mode, which this calculator is not. Okay. In this class, you need to be in radian mode at all times. Okay, there's never anything that we do that involves degrees. So I'm going to type in to y equals e to the negative x times cosine of x squared. Right, and then I'm going to graph this on the window negative 1 to 1. And notice that this derivative is strictly positive the entire closed interval. Okay, it's And you could tell that just by analyzing. This is always positive, and cosine is definitely positive on the theta interval -1 to 1, which is going to be the same as the x squared interval -1 to 1. So since the derivative is always positive, f will have its minimum value. I'm just going to grab a scrap for this one. I'm going to say f has its minimum value on the closed interval -1 to 1 at x equals -1 because f prime is positive the entire time, meaning f is increasing the entire time, so the absolute minimum would have to be at the starting point if it was increasing the whole time. Okay, this is a sufficient explanation, and at this point, as we move forward through the course, I'm going to want all of your explanations to be around the sign of something, something being positive or something being negative. But hold on, what was I thinking? Oh, if you said f is strictly increasing on that interval based on that, that would still be true, right? That would be something we could add in. So the left edge is the minimum if it's strictly increasing as we move left to right. All right. Number 6. What is the absolute minimum value of, it's a short enough question, I'll just be able to squeeze it up here, of the absolute value of x plus 2 absolute value of 1 minus x for -2 to 2. Okay, this is an interesting function. I think if you were to, maybe I'll graph this one for you in a couple of minutes and show you that it's a strange looking function. Okay, it's one that you might not have considered in the past. I think I only came to know this type of function when I taught college algebra. They had some in the college algebra book. I thought they were really nice looking. So if this is what I'm remembering, but I think it is. So what we're going to do is we're going to we're going to call this f. Okay, now we don't know how to take the derivative of absolute value. Okay, I'll just in case you're curious, in case you got here and like, hey, how do I take the derivative of absolute value? I will give you the rule right here. Okay, so the derivative of the absolute value of u is equal to absolute value of u divided by u times the derivative of u with respect to x for the chain rule, right? Okay, so it's that. We've seen that before, multiplied by the derivative of the inside for the chain rule. So that's, well, I'll just let you think about that. We don't need that. I'm not going to actually use that because I know that my critical points are places where the derivative is 0 or undefined. Regardless of what the derivative is here, these things are linear. So their derivatives won't be 0. Okay? Their derivatives can be undefined at those sharp corners, which happens here at x equals 0 and there at x equals 1. So I'm going to say my critical points are x equals 0 and x equals 1. Okay? I'm going to consider the endpoints as well. So x and absolute value of x plus 2 absolute value 1 minus x. All right, and I'm going to start with -2 and 2, and then I'm going to plug in 0 and 1. So what am I doing? Okay, just plugging in. 2 plus 2 times 1 minus -2 is 3, so that's 6 and 2 is 8. Like this arithmetic, I can do this, right? 2 plus 1 minus 2 is -1. So 2 plus 2 is going to be 4. And 0 would be 0 plus 2 times the absolute value of 1, which is going to be 2. And then when I plug in 1, I'll have 1 plus 2 zeros. All right, so it looks to me like the absolute minimum value on that interval is 1, which also happened to happen at x equals 1. which is coincidence, but not something that would happen on the quiz. So since we're talking about the graph of this thing, I'm going to just bring this in here. Okay, we just graphed that earlier. That is not what I'm interested in. I'm interested in the absolute value of x. That's in math number. That's absolute value of x plus 2 times the absolute value of 1 minus x. And we'll zoom to the standard window. And I think this is going to have two jaggedy things. Oh, no. Okay, we can't see this all that well. What we want to do, I'm going to take a risk and just zoom in here. Come on. Yeah. Okay, see, maybe I'm going to just shift the window to 0 to 5 instead of -2.5 to 2.5. So now see, it's doing one thing, then it bends, and then it bends again. Okay, that's an interesting graph. Okay, I've seen also one where it goes kind of like down, up or something, and I think you would need 3 pieces to make that happen. And I don't really exactly remember how that went, but that's a weird graph. It's not something, I doubt that's something you saw in your pre-calculus or your Algebra 2 class. But it's also not something you're going to need for this class past that problem. So, all right. A rectangle has one side on the x-axis, and its upper 2 vertices on the graph of y equals cosine x, as shown in the figure. What's the maximum possible area of the rectangle? Ooh, I like this one. This is a good problem. All right. I think what I'm going to do is I'm just going to push a lot of the statement of the question out, I think. That's y, so maybe I'll even just kind of... So that means that the height of the rectangle is given by cosine x. And the width, I think, is going to be 2x, right? Because you've got this x here and then another one over there. So my area equals 2x times cosine x. And if I want to maximize the area on the interval O, I also like this problem because we need to know the x-coordinates of these points. They don't tell us that. Good problem. So this is going to be x equals pi over 2 because that's where cosine goes 0. Okay, I'm just going to remind you off to the side, kind of right up here. Right, cosine is 0 here and there. Right? And so here we're looking on either side of the y-axis, so it's going to be pi over 2 and negative pi over 2. All right. Area is equal to 2x cosine x. We want to maximize that on the closed interval negative pi over 2 to pi over 2. So area's derivative is equal to 2 cosine x minus 2x sine x for the product rule. And, okay, I've got all this going. And I need to find where this is equal to 0. And I can't factor that. Maybe this is a calculator question? Let me think about it. Is there any way that I can factor this? No, I don't see the factoring. I don't see that happening. Unless there's some sort of trig situation. That would be 0. It's not 0 at x equals 0. Okay, right? Because 2 times cosine of 0 is 2, and then minus 0 would be not 0. All right, I'm not thinking of any on the unit circle, and I feel like I've got a pretty good idea of solutions to trig equations on the unit circle. So I'm going to go over here, and I'm going to bring in the calculator, and I'm just going to solve this equation on that closed interval. So 2 cosine x minus 2x sine x on the interval negative 0.5 pi to 0.5 pi. And then we are going to graph the thing. That's not what I want to happen. Okay, if it's ever graphing and you want it to stop, especially if it's one that's going to take a long time, you can press like the off key, you know, press second and then on, and it'll stop it from graphing. So that now I can go over here into my window, and I've got the x's set right, but I need to go give myself some negative space and y so I can find the zeros, because that's what I'm interested in. Where's a prime equal to 0? There's a place where it's equal to 0. I feel like it might come back and have another one. Yeah, and it's going to be symmetric because of the symmetry of the original and the symmetry of the problem. So I'm going to calculate a 0. I really am only going to need one of them. Left bound 0, right bound, say 1. Okay. And that's 0.8603. Okay. Now in this class, you probably want to copy all these decimals, and we do round to 3 decimals, but only in the last step. So I'm going to say x equals plus or minus 0. I'm interested in a prime equals 0. 0.8603359. 8603359. Okay. Those are the solutions to a prime equals 0. Now, I also know, looking at the graph of a prime, that this is a relative minimum on area, and this is a relative maximum on area, right? But I think it actually, our choice of x is going to be irrelevant, right? Because our choice is actually like, you know, how far over does this rectangle go? And then necessarily it goes to the other side. So I guess I probably could have maximized this on 0 to pi over 2 also, but it's going to be the same thing. All right, so I'm going to use the positive one because that's where I have a relative maximum. And so what I'll do is I'll say that the boundaries. Area when x is pi over 2 is going to be 2 times pi over 2 is pi times the cosine of pi over 2, and that's no area. Okay, so I know that the maximum is going to happen, you know, a of 0, also 0. You know, I'm not sure what my closed interval is supposed to be, but I'll just say that's negative pi times 0, which is also 0. So, you know, exhausted all the candidates except for area when x is 0.860333359. 3 3's, right? Yeah. And I'm going to plug that into my area formula using this device. And I'm going to say, well, so I'll show you something else you might not know about the calculator. Okay, I'm going to type it into y1, 2x cosine x. And then what I can do is have it, so because I would have to type in that number twice, one for this x and one for that x. What I can do instead is I can go call on y1 by going to, I think it's F4, yes. So you call on y1 and you plug in 0.86059, and it thinks, it knows what you mean. It's smart like that. It thinks you mean f of x, right? F of a of 0.860333359. You press enter. We're in radian mode. We're going to get 1.122 units of area, and that's our maximum amount of area, right? And we round to 3 decimals. 1.122 units of area is the maximum amount of area. Okay. And, you know, in the interest of time, this is already a pretty long video. I've got more meetings I need to go to today. I'm going to just continue moving. All right. Must there be a value of x at which f attains a maximum value on the closed interval -3 to 4? Justify your answer. Okay, well, okay, the must there, that means that this is an extreme value theorem question. Okay. And remember, the extreme value theorem says that a continuous function on a closed interval must take a maximum and a minimum. Okay? So the question here is kind of a disguised version of, hey, is this thing continuous? Probably at x equals 0. That's what we need to check. Okay, so the question is f continuous at x equals 0? Because otherwise, hold on, -3 to 4. Yes, -3 is the boundary of the domain for this, right? We can't go more negative than -3, because then, if it was -5, I'd be taking 9 minus 25 inside the square root, and we're not going to do that in this class. So what we need to do is, the limit as x approaches 0 from the negative side of f is equal to the square root of 9 minus 0. And that's 3, right? Because I just plug into the one where x is less than 0 if I'm approaching from the negative side. The limit as x approaches 0 from the positive side of f is equal to, well, I'm going to plug this in, -0 plus 3 times the cosine of pi x divided by 2. Well, I plug in 0, and this is going to be cosine of 0. Oh, but cosine of 0 is 1, so I'm going to say that's 3. Okay, and since these agree, and hold on, which way? This one is f of 0. Okay, they're all 3 the same. That means f is continuous. Okay. On the closed interval -3 to 4, so yes, f must have a maximum value. And I might say on the closed interval -3 to 4. All right. That's a good question. I like that. Good homework problem. A rectangular area is to be enclosed by a wall on one side and fencing on the other 3 sides. That's something I'm going to need to be drawing a picture of. If 18 meters of fencing are used, what is the maximum area that we can enclose? Well, I don't know. So I'm going to draw a picture of this. Okay, there's the wall, and here is the fencing. So I'm just going to call it X, Y, Y. 18 meters of fencing are used. That means X plus 2Y equals 18. What is the maximum area that can be enclosed? All right, well, so area is equal to X times Y. What we're going to need to do here is we're going to need to substitute on one of these variables, so it's just a 1 for us to maximize, because this is a single variable calculus course. If you take multivariable calculus with me next year, we'll take problems very similar to this, and we will take a completely different approach to them that, I don't know, this problem I might like just doing the substitution better anyway. But for now, what we need to do is we need to eliminate one of the variables, and I think what I'm going to do is I'm going to want to substitute on X here by solving for that X. So I'm going to go over here and I'm going to say, well, wait, X equals 18 minus 2Y. So if I distributed it in X times Y, this would be, distributing a Y on that, and that's going to be 18Y minus 2Y squared. Now this is the type, this is a downward facing parabola, right? A versus Y. And A of Y, and so it will have a maximum value. So this is looking promising, right? So, what am I? Okay, yeah, just find maximum value of A. And so it's just going to be, looking for A prime of Y equals 18 minus 4Y to the first. That's equal to 0 when Y is 18 divided by 4. Right? That's the only critical point, and it's a maximum, so it's going to be the absolute maximum. What am I thinking? Oh, X plus 2Y equals 18. Okay, so 18 over 4, I'm going to just call that 9 over 2. And X plus 2Y equals 18. So X plus 9 equals 18. That's x equals 9. We said y was 9/2. And that's going to provide us our maximum amount of area. Was that actually what they asked? No. They asked what is the maximum area that can be enclosed. So what we need to do is we need to say the max area. Yeah, just in view. There was an 18y minus 2y squared there, but a max is going to be equal to 9 times 9/2 is 81/2 square units of area. No, square meters. Because he said, yeah, 18 meters of fencing. All right, the volume of a cylindrical tin can with a top and bottom is to be 16 pi cubic inches. And we want to minimize the amount of tin, which I think we are going to say that's like we're going to minimize the area, the surface area of the cylinder. All right, but I am running out of paper. Hold on, I'm going to just... need more room to write. So the cylinder is like circle on top, circle on bottom, vertical sides. So the volume, which, you know, if you have to go look up the volume of the cylinder, that's completely all right. You know, this is the homework. It's pi r squared h, where that's the radius and that's the height. Okay. Volume equals 16 pi. Okay. Just something that I know I want to do right now is I'm going to just cross these out, and I'm going to say r squared multiplied by h needs to equal 16. Okay. But that's not volume. Okay, so I'm just going to say r squared h needs to equal 16. Now, we want to minimize the total area. Okay, so area is equal to... what's it going to be? It's going to be pi r squared plus, okay, if I was to like cut this thing out and open it up, you know, the side of the can, it would have a height of h, and this length would be the circumference of those circles, and so that would be 2 pi r. So plus 2 pi r h. All right. So what I should do is I'm going to need to substitute on h because I'll only have to substitute one place. And if I solve for r, then I would have to have r squared and r ready to substitute, and that's just strategically not going to be the thing to do. So what I do want to do is solve for h, solve for that h, and then substitute here. But I think that'll be pretty all right because h is 16 over r squared. Not too hard. And now, area depending on r is equal to 2 pi r squared plus 2 pi r times 16 over h squared, r squared, pardon me. Because I was substituting on h, 2 pi r h, yes. Okay, so this is, I'm going to need to simplify this. 2 pi r squared plus, I'm going to factor out the 2 pi. I don't know, I'm just taking a risk. I haven't worked this problem in a year or maybe two. So 2 pi r squared, I'm factoring out the 2 pi r squared plus 16 divided by r. And, well, I'm going to need a prime is going to be, well, that same 2 pi multiplied by, and this is 16r to the negative 1, so 2r minus 16r to the negative 2. Obviously, radius equals 0 is going to be a critical point, but radius equals 0 doesn't really make sense for our situation because the volume needs to be 16 pi, so that won't work. So now what I've got is, and I've got this equaling 0, because that's what I'm interested in, a prime equals 0, so that is not going to ever equal 0, so this needs to equal 0. So 2r minus 16 over r squared needs to equal 0. And could it be, oh, I see where this is going. It's going to work out nice, right? Because it's going to be, if I get a common denominator, that'll be 2r to the 3 over r to the 2. And I'll have 2r to the 3 minus 16 divided by r to the 2. I want that to equal 0. It only happens when the numerator is 0. And so that means that I need r equals 2, right? Because if r equals 2, then 2 to the 3 is 8. 8 times 2 is 16. 16 minus 16 is 0. But you could, if you wanted to, start by multiplying both sides of this equation by r to the 2, adding 16 divided by 2, and taking the cube root, if that's how you feel. Okay, but they did not ask for the radius, they asked for the height, right? What must be the height of the can? And since it's the only critical point, I know it's going to be a maximum, and it's going to be the maximum. And in the interest of time, I'm going to say h is equal to 16 over r squared is 16 over 4 is equal to 4. All right. The graph of f prime is shown at right, except I covered it up. On the interval -3 to 2, so I'm only interested in the function between those two vertical bars, and I don't know if I was smart to do that. Actually, what I'm going to do is I'm going to cover it up, and I'm going to kind of reproduce it. Okay, so it's strictly negative, and then it's strictly positive. Pardon me, I didn't do a great job of that. That's okay. And so this is -3. That's 2. This is the graph of f prime. F prime exists everywhere, so the function is continuous. F is continuous, differentiable because the derivative is defined everywhere. So if it's continuous on the closed interval, it has to take a minimum value. Okay, where does it take its minimum value? I think, okay, f is only decreasing and then only increasing. So I'm thinking that f is going to take its minimum value right there at the 0, which was at -1. Because f prime is only negative, then only positive, or f is only decreasing and then only increasing. All right, last one. The graph of y prime is shown at left. What value of x makes y the greatest? Okay, so on -2 to 2. Okay, this is another only critical point situation, so it only increased, then only decreased, right? So it only increased, and we don't know if it's like that. Like I was saying in lecture, I don't know if it's like that or like that. You know, if the amount of increase or the amount of decrease was greater. But what I do know is that the absolute maximum is going to happen at this relative maximum. So I'm going to say x equals 0 makes y the greatest. And that's going to be all for this video. That was a lot of closed interval tests, a lot of absolute maxima. I think that was a good amount of practice. But remember, if you watch all the way to the end, I hope you're not concerned about, oh, there being a bunch of absolute extrema on the Unit 3 test. Because there's just one multiple choice where you do the closed interval test and one free response where you do the analysis, because there's either 1 or 0 sign changes on the derivative. As we move forward in the course, we'll be using the closed interval test regularly in lots of units moving forward. But for now, we're just really getting our feet underneath us, getting used to the idea of an absolute maximum. Thanks for watching.